Okay, these are the notes for 7.1 and 7.2 compound interest, 7.3 using functions involving e. All right, so this is a little bit different from what we've been doing before. Before, when we were doing exponential functions, we were using the parent function y equals to the x. X represented time. For real-world applications, though, time doesn't just jump from one year to the next year and things like that. So, for example, when we talk about banks paying interest on like your savings account, they're not just going to calculate your interest in one-year increments. They're going to compound interest by quarters, maybe by months, things like that. So we're going to separate the increments of time. So because of that, we're going to change up our formula of how to calculate a total amount, still having an initial amount called the principal, right? And this is going to be your growth rate in here. This time we have to separate the rate and divide by the number of times that we're going to be calculating the interest, or other words called compounding the interest. And then we're going to raise it to the number of times we're going to compound over total number of years. So we've had to alternate our formula to take into account that we're not just jumping from one year to another year without any time in between. Okay, so it gave you the breakdown of what each letter means. Again, P is the initial amount, right? R is the interest rate. This is your growth rate. And then N is the number of times interest is calculated per year, and T is still for time in years. Okay, so we're going to do some examples using the same initial amount here in the table. All right, so we're calculating if our initial investment is $1,000 in every single scenario. Annual means we're only compounding one time a year. Semi-annual means we're compounding twice a year, right? Quarterly is 4 times a year, and so on for the rest of these. So if you substitute all your values into this generic function here, right, we're going to get back some different values because we're compounding differently. The more times you compound a year, the more money you will make, the faster it will grow, right? Because it's affecting your growth rate and also the exponent, how we're raising your growth rate, right? So go ahead and plug in some different values, right? So this is going to give back something. I'm going to help you start this one, right? So if we do quarterly, our initial amount is still 1,000. We're still doing 1 plus 0.1 on top because we're talking about a growth rate of 10%. So 10% as your number is 0.1. On bottom, because we're compounding quarterly, that's 4 times a year, you can put 4 on bottom. And then up as your exponent, we're compounding quarterly, so 4 times a year, and we're talking about a 1-year time frame. Okay, so you guys fill out what each of these are going to be and the equations. Okay, so check your work, make sure that we've done some good substitution into our generic formula, right? And these are the values that you get back after rounding appropriately for dollars and cents. So you can see the more times you compound your interest, the more money you make. With it just staying in the bank for 1 year, right? It's not growing super fast. Remember on our exponential function and when we did our lab BuzzBugs, there was really small growth in the first 3 shakes. And the longer you, the higher shakes you did, the more shakes we did, then it started growing exponentially more, right? So the growth is bigger the longer period of time. So this looks small, but think about longer periods of time. So our next example is going to be talking about more than just 1 year. Okay, so our next example is talking about Ben, who deposits an initial amount of 500, right? So that's our P value in his savings account. The account pays interest at 7%. 7% is the rate, but you have to convert it to a number, which is 0.07. Right? It's compounded quarterly, right? This is the number of times it's collecting interest a year. So quarterly means 4 times a year. Time is overall time, and overall time is 3 years. He wants to know how much he's going to have after 3 years. So that's what each value is, and then you're going to substitute it into your generic formula that we had in the front. So you're going to get back that the total amount is going to be using this equation. Make sure that when you're using the calculator that you're using parentheses just like I've written them. Okay, so when you put that in the calculator, we're going to get back that the amount is around 615.719, and then we have to round appropriately for dollars. So after 3 years, he's going to have $615.72. Okay, our next example, we're going to have a higher initial amount, right? This time our starting amount is something actually we don't know. It says, how much would you have to invest to have 20,000 after 6 years? So that means my A value. After 6 years, I want this much money. I don't know what I have to start with. I want the total time to be 6 years. And the growth rate is 8.5%. So the rate as percent is 8.5 like this. We have to change it to a number. So we'll move the decimal over 2 places, right? And we get 0.085. And it's supposed to be how often it is collecting interest, and they say it's being compounded monthly. So that means 12 times a year. So when we set it up into our generic function, this time we're going to have 20,000 equals my principal amount, which is, I don't know, 1 plus 0.085 over 12 raised to 12 times 6. All right, so this is what we have. I'm trying to solve for P. Recognize that all of this part right here is just a number. There's no variables in that. So you can actually calculate this. So 1 plus this fraction raised to this power is going to give you back 1.662 and a lot of decimals. We don't want to round yet, right? We're going to store this in the calculator, right? So now to get P by itself, what I need to do is divide both sides by this 1.662. Okay, so in the calculator, you have this stored. So you're going to do 20,000 divided by this stored number and get that P is $12,031.52. All right, the next thing that we're moving towards is what would happen if we compounded continuously. So when you think about continuously, that means not just monthly, not just daily, not just secondly. We're always compounding, right? We're doing that all the time. So to talk about what that's like, we have to talk about the number E. Just like pi is a number, 3.14, et cetera, E is also a number. So we're going to do this table to try to figure out what E is. So here's your function 1 plus 1 over n to the nth power. And then we're going to substitute 10 in, right, for your n's and get a number, right? And then you're going to substitute 100 in and get a number. So I'm going to let you guys fill out that using your calculator. Okay, so after you fill it out, it looks like this. So E is like pi, where the decimals go on and on and on without repetition. It's an irrational number, right? As your n value gets bigger and bigger and bigger, your E value starts approaching a certain number. That certain number is this number. So in the calculator, we actually have an E button. So you guys could do second divide by key, and there's the E value. Right? That's what your calculator is using every time you type in E. Right? So it's approaching that number. So every time we get bigger and bigger, right, we're approaching this number E. Just like pi is a ratio of circumference and diameter. Okay, so now let's flip to the other side. Okay, so E represents a certain number, right? We have to get comfortable working with E. So some number squared times another, the same number, same base, to the 5th power is still going to be E, right? And we're going to have to figure out the power by our power rules, which means we're going to be adding those to get 7. We're going to leave it like that and not actually convert it into a decimal, right? Just like in geometry, you left your answers for circumference and area in terms of pi. We're leaving this in terms of E, so there's no rounding involved. All right, same thing with this, right? To simplify this, right? 3 goes into 12 4 times. This is like having 4 e's on top, 3 e's on bottom, so we're going to have some cancellations. Or you can think of your power rules. 4 minus 3 leaves an e to the first power, and this reduced to 4. Okay, and then on number 3, we have this quantity being squared, so you have to square each part, right? So 5 squared is 25. And then we use our power rules, right? So if you have a power being raised to a power, you actually multiply. So this is e to the negative 6x. And then we're going to have to simplify this because we can't have negative power. So I have 25 on top and e to the 6x on bottom. Okay, so the whole point of e was this is what our growth rate would be like if we could compound continuously every nanosecond, even smaller than nanoseconds. If we can compound continuously over time, there were no increments, then we would use this formula, P e to the RT. Again, P is principal, E is our growth rate, that is a constant, R is the rate, and T is still time. Right, so we don't have to have the n anymore because we're compounding continuously over time. So application problems here, Terry deposits $100, right? So that's our initial amount for his 5th birthday. It compounds continuously. So there's that word continuously. That reminds me that this is the formula that I have to use now. The rate is 5%. 5% as a number is 0.05. Okay, the time is going to be, we're doing this until he turns 21. So 21 minus 5 is 16 years. So we're going to substitute in our formula. For short, I'm going to call it PERT, right? So we got 100 e to the 0.05 times 16 is back $222.55. All right, in our last example, suppose you invest $1,500, so that's my initial amount, at an annual interest rate of 9.5%, so 9.5% as a number is 0.095. It's compounded continuously, so that means we're going to be using the PERT format, and its time, total time is 25 years. So we're going to substitute into PERT, and we get... right, this equation, right, you put that into the calculator and we get the total amount after all this time is now $16,126.52.